When alternating current, AC conductors are run in parallel and grouped by phase through separate ferrous, that is steel or iron, chase nipples. The surrounding metal cabinet can experience significant heating. This phenomenon is due to the interaction of magnetic fields and the generation of eddy currents within the metal enclosure. To understand this, it's crucial to delve into the principles of electromagnetism and how AC current behaves in conductors. Firstly, every current-carrying conductor generates a magnetic field around it. The strength of this magnetic field is directly proportional to the magnitude of the current. In the case of AC, the current is constantly changing direction and magnitude, which means the magnetic field is also constantly changing. Secondly, when multiple conductors carrying AC current are placed in close proximity, their magnetic fields interact. The nature of this interaction depends on the phase relationship of the currents in the conductors. In a balanced three-phase system, like the one implied here with A, B, and C phase conductors, the currents in each phase are 120 electrical degrees apart. Thirdly, the problem arises when you group conductors of the same phase together through a ferrous chase nipple. Because the conductors of the same phase are carrying current that is in phase, their magnetic fields will reinforce each other. This creates a stronger, concentrated magnetic field around the chase nipple compared to a scenario where conductors from different phases are mixed within the same nipple, or if the conductors were not enclosed in a ferrous material. Fourthly, the concentration of a strong, alternating magnetic field around the ferrous material like the steel chase nipple and the surrounding metal cabinet is where eddy currents come into play. According to Faraday's law of induction, a changing magnetic field induces a voltage in any nearby conductor. This voltage, in turn, drives current flow within the conductor. In a solid piece of metal, these induced currents circulate in closed loops within the material, hence the name eddy currents. Fifthly, the flow of eddy currents within the metal is not without consequence. The metal has a certain resistance to the flow of electric current. As eddy currents flow through this resistance, they dissipate energy in the form of heat. This is known as joule heating or resistive heating. The amount of heat generated is proportional to the square of the current and the resistance of the material, described by the formula P equals I squared R, where P is power or heat generated, I is current, and R is resistance. Sixthly, the heating effect is exacerbated by the properties of ferrous materials. Ferrous metals, like steel, have high magnetic permeability. This means they concentrate magnetic fields more effectively than non-ferrous materials like aluminum or copper. The higher the magnetic permeability, the stronger the induced magnetic field and, consequently, the larger the eddy currents and the greater the heating. Seventhly, the thickness of the metal also plays a role. Thinner metal offers less resistance to the flow of eddy currents, which might seem counterintuitive. However, thinner metal also has a smaller cross-sectional area for the eddy currents to flow through, effectively increasing the current density. This higher current density leads to increased resistive heating. Eighthly, the frequency of the AC current also affects the magnitude of eddy currents. Higher frequencies result in more rapid changes in the magnetic field, which induces larger eddy currents. In the United States, the standard AC frequency is 60 Hz, but in other countries, it might be 50 Hz or another frequency. Ninthly, one way to mitigate this heating is to use non-ferrous chase nipples, such as those made of aluminum. Aluminum has a much lower magnetic permeability than steel, so it does not concentrate the magnetic field as effectively, resulting in significantly reduced eddy current losses and less heating. Tenthly, another approach is to ensure proper spacing between the conductors. Separating the conductors reduces the interaction of their magnetic fields, thereby lowering the overall magnetic field strength around the chase nipple. 11thly, using a larger chase nipple can also help. A larger nipple provides more surface area for heat dissipation and can reduce the concentration of the magnetic field. 12thly, an alternative is to use individual entry points for each conductor. Instead of bundling the conductors through a single chase nipple, each conductor can have its own separate entry point into the cabinet. This minimizes the interaction of magnetic fields. 13thly, another very important consideration is to ensure that the electrical installation complies with all applicable codes and standards such as the National Electrical Code, NEC, in the United States. The NEC provides guidelines for conductor sizing, spacing, and installation methods to minimize the risk of overheating and other electrical hazards. 14thly, it's crucial to verify that the conductors are properly sized for the load they are carrying. Overloaded conductors generate more heat, which can exacerbate the eddy current heating effect. 15thly, regular inspections of electrical equipment are essential to identify and address potential problems before they lead to equipment failure or safety hazards. Look for signs of overheating, such as discolored wiring, melted insulation, or a burning smell. 16thly, consider the impact of harmonic currents. Non-linear loads, such as electronic devices, can generate harmonic currents, which are multiples of the fundamental frequency 60 Hz. These harmonic currents can exacerbate eddy current heating due to their higher frequencies. 17thly, filtering or mitigating harmonic currents can reduce the risk of overheating. This can be achieved through the use of harmonic filters or by using equipment designed to minimize harmonic generation. 18thly, ensure that the metal cabinet is properly grounded. A good ground connection provides a low impedance path for fault currents, which can help to prevent dangerous voltage build-up and reduce the risk of electrical shock. 19thly, consider the ambient temperature in which the electrical equipment is operating. High ambient temperatures can reduce the ability of the equipment to dissipate heat, which can increase the risk of overheating. 20thly, providing adequate ventilation around the electrical equipment can help to dissipate heat and keep the equipment operating within its temperature limits. 21st, you could use sterating factors. When multiple conductors are bundled together, their ampacity, or current carrying capacity, must be derated according to the NEC. This derating accounts for the increased heat generated by the bundled conductors. 22nd, using thermal imaging cameras can help detect hotspots in electrical equipment. These cameras can identify areas of excessive heat, which can indicate potential problems such as loose connections, overloaded conductors, or eddy current heating. 23rd, torque connections properly. These connections create resistance, which generates heat. Ensure that all electrical connections are properly torqued to the manufacturer's specifications. 24th, consider using liquid-filled transformers and equipment. Liquid-filled equipment often has better heat dissipation characteristics compared to dry-type equipment. 25th, when using parallel conductors, it is essential to ensure that all the conductors are of the same material, size, and length. This ensures that the current is evenly distributed among the conductors. 26th, regularly clean electrical equipment to remove dust and debris. Dust and debris can act as insulators, which can trap heat and increase the risk of overheating. 27th, use surge protection devices to protect electrical equipment from voltage surges. Voltage surges can damage equipment and cause overheating. 28th, consider using energy-efficient equipment. Energy-efficient equipment generates less heat, which can reduce the risk of overheating. 29th, when installing electrical equipment, follow the manufacturer's instructions carefully. Improper installation can lead to overheating and other problems. 30th, regularly train employees on electrical safety procedures. Training can help employees identify and address potential electrical hazards. 31st, perform routine maintenance on electrical equipment. Regular maintenance can help identify and address potential problems before they lead to equipment failure or safety hazards. 32nd, keep accurate records of all electrical work performed. These records can be helpful for troubleshooting problems and for planning future maintenance. 33rd, consider using a power quality analyzer to monitor the electrical system. A power quality analyzer can detect problems such as voltage imbalances, harmonic distortion, and transients, which can contribute to overheating. 34th, implement a formal electrical safety program. A formal program can help to ensure that all electrical work is performed safely and in compliance with applicable codes and standards. 35th, ensure the metal conduit is properly grounded. The grounding path should have low impedance to carry any fault current and protect personnel. 36th, the selection of the right cable type is essential. Choose cables that are designed for the specific application and environment. For example, some cables are designed to withstand high temperatures or exposure to chemicals. 37th, implement a lockout-tag-out program. Lockout-tag-out procedures are used to ensure that electrical equipment is de-energized before any work is performed on it. This helps to prevent electrical shock and other hazards. 38th, always wear appropriate personal protective equipment, PPE, when working with electrical equipment. PPE can include items such as gloves, safety glasses, and insulated tools. 39th, never work on energized electrical equipment unless it is absolutely necessary. If it is necessary to work on energized equipment, follow all applicable safety procedures. 40th, be aware of the potential hazards of arc flash. Arc flash is a dangerous electrical explosion that can occur when there is a fault in electrical equipment. Arc flash can cause serious burns, blindness, and even death. 41st, perform an arc flash hazard analysis to determine the potential arc flash hazard levels in the workplace. This analysis can help to identify the appropriate PPE and safety procedures to use. 42nd, install arc flash protection devices to reduce the risk of arc flash. Arc flash protection devices can include items such as circuit breakers, fuses, and relays. 43rd, always maintain a safe working distance from energized electrical equipment. The safe working distance depends on the voltage of the equipment and the potential arc flash hazard level. 44th, never block access to electrical panels or equipment. Blocking access can make it difficult to shut off the power in an emergency. 45th, ensure that all electrical panels and equipment are properly labeled. Proper labeling can help to identify the equipment and its voltage. 46th, never use damaged or frayed electrical cords. Damaged cords can pose a serious electrical shock hazard. 47th, never overload electrical circuits. Overloading circuits can cause the wiring to overheat and start a fire. 48th, use ground fault circuit interrupters, GFCIs, in wet or damp locations. GFCIs can help to prevent electrical shock by interrupting the flow of current if a ground fault occurs. 49th, test GFCIs regularly to ensure that they are working properly. GFCIs should be tested monthly. 50th, never run electrical cords under rugs or carpets. Running cords under rugs or carpets can damage the cords and create a fire hazard. 51st, never use extension cords as a permanent wiring solution. Extension cords are only intended for temporary use. 52nd, never remove the grounding pin from an electrical plug. The grounding pin is there to protect against electrical shock. 53rd, be aware of the location of underground utilities before digging. Digging near underground utilities can damage them and create a safety hazard. 54th, call 8.11 before you dig to have underground utilities marked. 8.11 is the national call before you dig number. 55th, use only approved electrical equipment. Approved equipment has been tested and certified to meet safety standards. 56th, report any electrical hazards to the appropriate authorities. Reporting hazards can help to prevent accidents and injuries. The concentration of same-phase conductors through ferrous materials can create eddy currents, causing the heating of the metal casing and enclosures due to induced magnetic fields in response to current.